I'm going to talk a little bit about identity. It's a small pattern. I'm cheating a little bit. I'm going to talk about value objects and entities as well. Identity crisis. Well, you already had the introduction, so I don't need to explain that. We're going to try to model a little example here. This is a lesson schedule from a school. Well, probably not that school, but should work. And we're just going to try to get through modeling this the way we could build a system for that or a little domain model for that and see how we can, what we can learn from that. Before I talk about identity, well, there's a couple of things that you probably know or that you probably have been doing. You have been using IDs for probably as long as you have been programming. You have been using them to identify something. It's basically a little pattern that you use to communicate between two things, two systems, so you can communicate about the same thing without actually needing the thing itself. That's what an ID is, to talk to a database, to talk over an API to an external system. And there's a couple of concerns that you're probably going to use to decide whether an ID is a good choice. Well, maybe you're not using any heuristics for that. Maybe you're just slapping an auto-increment ID on there without thinking about it at all and just doing the same thing every time, which works to some degree, but there might be more interesting ways of looking at it. So there's a couple of properties that an ID must have. It needs to be stable over time. If the ID changes of something, then you get into trouble because then you need to notify all the other systems that this ID has changed. This will get you in a mess. And it needs to be unique, or at least it needs to be sufficiently unique within its own context. This is why auto-increment IDs work. They are not unique, but they are usually unique within one context, for example, one table or one set of things, of domain objects. But let's try to avoid having as much theory, well, let's avoid having theory. Let's try to make it as much about practical things as possible. I can show you code if you guys want to, but I'll try to do it without. I think it's better and faster to learn to reason about code and learn to reason about patterns and all these things without actually seeing the code. But if it's going too fast, if you feel that you need some code, then raise your hand or we'll check in a moment. So this is a lesson schedule, right? And the book that Sean mentioned, Domain-Driven Design, advises to, when you're modeling something, when you're trying to implement some model in your code, the book advises to try to find value objects first. Try to make as much of this model encapsulated in value objects. And value objects are really great. They are very small. They're very small. They're very composable. They have like a single responsibility. They represent one piece of information in your model, one unit, one little bit of one value basically, or one sort of small combination of values. So typical examples are things like temperature. Temperature is not a number. It's not 5 or 20 or something like that. If I say it's 20 outside, well, maybe from the context you could guess it, but this is not a very scientific way of saying that what the temperature is. If I say it's 20 degrees Celsius, then of course you know what I'm talking about. You know the sort of unit of measurement, right? So this is something that a good domain model, we try to capture these kinds of things. So instead of representing this temperature, if we're trying to build some system like a weather application, for example, instead of representing this temperature with an integer or, well, a float maybe, that's not giving us a lot to hold on to. We can wrap this. We can say, wait a minute, temperature is a concept in our domain, so we can try having an object to represent that concept. That's one of the ideas in object-oriented programming. You find things in your domain, in the problem space, in our case, weather, and you try to wrap some sort of make this concept explicit in your code and wrap this in some some kind of object, for example, especially in object-oriented. So we could make a little object, and we call it a little class called temperature. And it takes a value in the constructor. It takes a primitive, a float, which is the number. And maybe depending on how you implement it, you could also take the unit of measurement. So you could take Celsius or Fahrenheit or Kelvin. You also take this in the constructor. So these two things belong together. You cannot reason about temperature without knowing whether it's Celsius or Fahrenheit or Kelvin. But now, because you could do this with an array, but this is a thing that wants to be an object. That's something that you, like if you think about it, you could represent this with you could represent this as a string, but in object-oriented, we're going to represent this as an object. So now we have this small object that knows, that represents a temperature and represents whether it's Celsius or something else. The great thing is, because we have an object, this object can now attract behavior. This is sort of a little center of gravity. This is a place where any behavior related to temperature, any behavior that operates on this little value, any behavior that makes calculations with this little value, we can now push it into this value object. And this is very nice, because then we have, this is object-oriented programming. This is encapsulating state and behavior together in one place. Things that naturally belong together. For example, and this could be very simple, something like, is it freezing? This is a calculation. It's a very simple one, but it is a calculation. It is a bit of business knowledge. It's a bit of, well, not business, but domain knowledge about how temperature works. So this knowledge belongs as close as possible to the data. That's encapsulation. That's what it means. We're encapsulating data and behavior. So now I make a public method on this temperature object, and I can now ask this object, if somebody passes me a temperature object, I can ask it, are you freezing, or are you above freezing point? And then of course internally it's going to make a calculation. If it's in Celsius, it's greater or less than 0. If it's in Kelvin, it's 273, etc. So this little bit of business knowledge is, or domain knowledge is encapsulated. Other kinds of calculations, for example, converting between Celsius and Fahrenheit or Celsius and Kelvin, that's a very simple calculation again. But by putting it in this object, we have one place that you cannot get around it anymore. You cannot, if you type hint on temperature, then you never have to get the value out of this object and make the calculation yourself and then maybe put it back in or something. You can just ask this object. This is another principle that you may have heard of in object-oriented programming called tell, don't ask. We're not asking for the state of this object, doing a calculation and then giving it back. We're telling this object, hey, calculate this for me. You do the work. I'm just going to, use you for your behavior. So this is very nice because you get these very small objects that you can pass around. You can type hint on them, so you get fewer bugs in your system. If you can have a method saying, I accept a temperature object, then you're basically telling your client code, this is the contract. If you want to call me, you have to call me with a temperature object. I don't care what it looks like on the inside. I only care that it adheres to this contract of being a temperature object. So this object itself could be responsible for its own validation, its own consistency. It's responsible for keeping its own state, and it's responsible for any kind of behavior or calculation on top of this little object. Right. So this makes for a very powerful thing. It's very small. It's very simple to test. That's another benefit. How do you test this object with this behavior that I just described? Very simple. You write a test. You write a new temperature 20. And then you assert is freezing, should return false. Or if you do -5, is freezing, should return true. So it's very simple to test objects like these. And if you have, so if you start looking in your code or thinking about your domain, and you put a little effort in, you will find a lot of these kind of objects. They are very useful to sort of encapsulate behavior and then compose, as we'll see. So, well, that was again a little bit of theory. The one thing that maybe I should mention as well is the best way to implement them, these little objects, is to make them immutable. That's again something, it helps you to make your code very easy to reason about. If I have a value object that cannot change, and how do you make a value object immutable in PHP? Basically by not having any setters or not having any methods that change the value. Any method on there should give us a new value object as a return value. So you're making this immutable. This makes code very easy to reason about because objects are passed by reference in PHP. So if I pass an object to somebody, I know that this object cannot change. I know that this is very stable, I can just work with it. And again, this is modeling, in a sense, the real world. This is the same as in mathematics. In mathematics, the number 5 will always be the number 5, right? 5 degrees Celsius will always be 5 degrees Celsius. If it warms up outside, it's not that the number 5 has changed into 6. It means that it is now replaced by 6. This is how mathematics work. You assign something, you have a value, you have a number, it doesn't change, you just replace it by another. So this is another sort of very nice property of having these little value objects. So before I go on, can you sort of make a mental picture of how value objects work, how you could implement them without seeing code, or do you want to see, like, who wants to see code? Just okay, very few people. Well, I'll just quickly show some other example of. I think it's right here. So this is money. So basically, I'm constructing this with same kind of example. The amount and the currency, they belong together. It's not here's 5. It's here's 5 euros or here's 5 dinars or something. I store the values in this object, in the private properties, and then any behavior that I have on it. For example, money has some very specific behavior. You cannot add dollars and euros without a conversion. So here I'm throwing an exception. So this is a little bit behavior. I'm throwing an exception saying that I cannot add different currencies. If I'm trying to add 5 euros to $5, this code will fail. So this object is responsible for guaranteeing its own consistency rules. And that's not just value objects, all your objects should do that. If you have that, then that's again, this is object-oriented this is the heart and soul of object-oriented programming. You have small things that are consistent, that protect their own state, that only talk to other things through contracts that they agree to, and that are sort of small and composable and easily testable. That's how you should build your system. And so the other thing that we see here is that when I add this money to some other money, after it has made sure that this is a legal operation, so after this guard about currencies, it's not changing itself because my money doesn't change. I'm just returning a new money object. So there's a new value object that now has, of course, the sum of the amounts and the same currency. So is this making sense for the people who raised their hands? Is this sort of giving you enough to go on? Yeah? Okay, great. Smart audience. So let's take this. Let's do some actual modeling. Like, what's the thinking process that we would use to start building systems using this? And the reason, well, maybe I'm spoiling the surprise, but the reason I'm mentioning it, value objects, they have identity, but they only have identity defined by their value. So the money was a good example for that. If I have 5 euros, and I give it to you, and tomorrow you give me 5 euros back, I don't care if it's the same banknote. This could be a different banknote, could be coins instead of a banknote. But if the value is the same, then for all practical concerns, this is the same money. This is the same amount of money. It's the same value. So we care about this 5 euro object or this 5 degrees Celsius object purely because of its value. If I have 2 instances and they're both 5 euro, then I don't care if it's the same instance or a different instance. They have the same identity based on their value, right? And of course, this is going to be contrasted to things that We are not going to compare by value, and that will have some additional identity on top of that. So let's go to Hogwarts. This is the lesson schedule for the year 2014-15. For Group 1A, we have a couple of weekdays here, and from 9 till 10 in the morning, Teacher Jim is teaching an English class, and 10 till 11, Anna is teaching IT. So, given what I've told you about value objects, right? They're just these small objects that represent some value. And given what I've said before, that Eric Evans advises in his book to try to model problems with value objects as much as possible, right? So we're going to try to make a very simple model to represent this thing. That's all we're going to do for now. How can we represent this little structure here in code? Okay. So I'm going to get you guys to do a little bit of work now. Just take a minute and try to count or try to find as much value objects as you can in this picture. As much as possible, as much candidates for value objects as you can find in this picture. And just sort of count them, and then I will check how many you found. So take a minute. Okay, who found no value objects at all? Raise your hand. Okay, who found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I think we have a 12 there. We had 111, I think. Yeah, 111, 12, 13, more than 13. Who? More than 13? Who did not raise their hands? Okay. So we have quite a range here. Let's see what we can find. Well, if this was a smaller group, I could ask all of you, but there's a little bit too many of you. Let's try with some of the obvious ones. Like, let's take the weekdays, right? Did you find weekdays? Yeah. I think that's an obvious one. So this could be an object. You could, of course, represent this with just an integer or a string. That would be fine. I mean, that would work. But that doesn't give you a lot of flexibility. There's nothing you can do with an int or primitive. You cannot attach anything to it. You cannot type hint on it in PHP, which is. But even if you could type hint on string, then all you would know is that you get a string. You wouldn't know anything else about this string. So it's still sort of a very. So the value object weekday is sort of a subset of all possible strings. It's in some languages you have enums. You have it in relational databases as well. So this is basically a very small set of 5 possible values, and that's what my weekday value object is enforcing in this example. So that should be easy to implement, right? Of course, a weekday cannot change into another weekday. So again, this is immutable. Let's find some more. We had, let's say, for example, English subject. And IT and math, of course. Again, they could be represented as strings. They could be represented with some kind of key, but then we're sort of losing some information there. We could just say that this is a subject value object. Or maybe we could say a subject label, if we want to, or subject name, if we wanted to be very precise. We could do the same thing for the teachers, teacher name. Here I just have the first name, but you could have a teacher name or just a name object that actually consists of a first name and a middle name and a last name and maybe a title even. So you can sort of build these little compositions of multiple values that represent some concept. So the name of a person here can be represented by an object. Probably not much behavior that we will be able to attach to it, but that's fine. It's just we're just building up this structure here. In the same way, we could have the name of the school. That could be a value object. The name of the group, which is, in this case, it's 1A. This happens to be a name that has a little bit of more meaning to it, because from the name we know that it's the first grade, and it's the first class from the first grade. So we would have 1B if we have multiple groups of pupils in the same grade, something like that. A little more interesting, maybe here we have combination of times. Well, the time itself could be a value object. The 9 o'clock or the 10 o'clock, that's a value, right? That's not a daytime. You cannot represent this with a daytime. This does not have date information at all, so that wouldn't make sense. You cannot represent this with a daytime. So you could simply make your own object here that represents 9 o'clock. And kind of obviously, you can make a bit of a combination there. You can make a composition of the 9 o'clock and the 10 o'clock. They're both times, but this composition is, you could call it a period, for example. So this period is constructed using a start time and an end time. It even has some behavior. It has some validation. It can sort of protect its own business rules. What could that business rule be for a period? Any idea? Yeah, exactly. So the end time cannot be before the start time. Of course, in some domains, that would be possible. For example, if we have lessons that start at 11:30 in the evening and span until the next morning, then the end time would be before the start time, so to speak. It's not before, but we know in this domain, we know in schools and like primary schools that nobody is teaching at midnight. So it wouldn't make sense to allow our model to represent this state. So this is an interesting sort of concept here. If we can model things, if we can build a model that disallows illegal states, we're going to get a lot fewer bugs. We cannot prevent everything, but as much as possible. So we know that when we get an exception because somebody's trying to make a period from 10 till 9, that exception is telling us that there's some bug somewhere. Somewhere maybe we are swapping two values, right? So this helps. You make a model that limits the possible states in your system. That's what we're doing with all these value objects to some degree. The same thing with the weekdays, by the way. We know in this domain that nobody is ever teaching on a weekend, so we don't need a generic sort of weekday object that represents 7 days, or that can represent any of 7 days. We can limit this. You know, we make the set of possible values of legal values smaller. And again, all these values are sort of identified. All these value objects, they have identity that is only represented by their own value. A Monday is a Monday, right? Again, this is not a daytime. This is not a specific Monday at a specific point in time, in a specific month and date and etc. This is just the concept of a Monday, which repeats every week, unfortunately. So let's see, how many did we find so far? 1, 2, 3, 4, 5, 6, 7, if we count the combination of two times. We missed the school year so far. So a school year is not a year. It looks like a year, but it's different. It has some behavior. Where I come from, a school year always starts on September 1st. It always ends on June 30th. It's very fixed, but I know that in different countries this can sort of have more variation. So in this case it was fairly simple. Still, in a system, like in the system that we built this for, an education system, it turned out that school year was one of our biggest value objects. Internally it's very simple. You can represent this with just a start year, for example. Or you could represent this with a start date, or you could represent this with a start date and an end date, or a start year and an end year. You can choose any kind of internal representation, but from the outside, we don't care. This is information hiding. This is encapsulation. So we don't care what our object looks like on the inside. We care how it behaves on the outside, what kind of methods are on there. So this object could have, for example, a get start date, which would give us September 1st, 2014. But we don't care if this get start date method is a calculation or it's just returning some value that is already in that object. That doesn't matter. From the outside, we don't care, right? So we have this concept of encapsulation here. We could choose to represent this. So maybe there's two value objects. Maybe we have year or calendar year and then school year. And we could compose school year using calendar year. So maybe it's two value objects. Sort of depends on your choice of implementation. But it turns out there was even more, like, you can't imagine the number of behaviors that we attached to this school year object. There were all kinds of calculations. For example, what week numbers are in this school year. There's even complexity that there was in Belgium. They have calendar weeks, so week numbers, which start in January. Well, it sort of depends. There's even a little bit of a domain rule there that the calendar week, if it starts, I think if Thursday is January 1st or later, then the week counts as the last week of the previous year. And if January 1st is on Monday, Tuesday, or Wednesday, then this counts as the first week of this year. So there's a little bit of complexity there, but we're hiding that. If you have a year object or a school year object, you can just ask it for its calendar weeks without needing to know how this calculation works. So this helps with code reuse and with making sure that everything is, this is a single source of truth. So you can just tell by the number of patterns that I'm mentioning and principles that I'm mentioning how much value objects are sort of at the heart of object-oriented. All these principles apply there very well. So it's single source of truth because there's only one place that knows how to calculate calendar weeks. And the other complexity was that they also have school weeks, and school weeks don't start in January. School weeks start at number 1 in the week that has September 1st, and it's always the first week, so there's no like a Thursday rule there. And it was even more complex because in the holidays they stop counting. So it could be week 20, and then there's 2 weeks of holidays, and then it's week 21. So all this knowledge, all this information was encapsulated somewhere. So that's what I was saying. When if I had just made an integer, then all these calculations would be spread around somewhere. I could still group them in some service maybe, but there's no like a service class is pretty much a procedural construct. It's not really object-oriented. By making this value, this string or this int, this primitive, turn it into an object, it can attract all this behavior that sort of belongs to it, right? And again, a school year is identified by its value. This school year is different from this one, and this school year is the same one as the exact same one, as long as they have the same value, right? So identity is sort of implied here from the concept itself, if that makes sense. What else? We have, I think I can probably move to this slide. This shows most of the ones I mentioned so far, I think. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 so far. So who's still in the game? Who has 9 or more? A few people? Okay. Great. Let's see if we can find some more. We already had one where it's composed, right? Where this is a simple composition of 2. In this case, they're both time objects, but one is the start time and one is the end time, which is just like one is assigned to the start time variable and one is assigned to the end time variable. So, and there's a little bit of behavior there, and that's it. So it's a nice simple composition. We can probably find some more ways to compose things here. For example, when Anna teaches IT, that's different from when, let's say, Jim would teach IT. So there is a difference there. These two things, who is teaching what, that sort of belongs together. We could call that a class, for example. So a class is, for example, IT taught by Anna or English taught by Jim. Both of those concepts could be a class. Not a class in the term of like PHP classes, but a class in the school, in the education domain. But we could have other combinations. For example, what's happening here, right? Every Tuesday from 9 till 10, that could also be a value object. This is a concept. So this cell itself, the cell is a value object, or could be. Well, it's a choice, of course, but we could represent this as a value object. So this object is a composition of a weekday and a period, and we could call this a slot, for example, or maybe like I'm not sure about the language in English. It could be that I'm sort of messing it up, and that this is a slot, and that the combination of a slot and a weekday is a period. Maybe that makes more sense. So, but that's something that you can figure out by talking to the people in the domain. They have names for this, so you don't have to invent this. You can sort of talk to people and figure out what do you call this combination. Oh, that's a period, right? And then you know how to name your code. So when people say that one of the hard problems in programming is naming things, well, just ask a domain expert, right? Of course, then you have to talk to somebody, so it is hard. I agree. Okay, so we have this cell is some point in time, basically. It's not just horizontal or vertical, it's the combination. So, and it is not one very specific point in time in terms of, January 20th at 9 o'clock. It's every Tuesday at 9 o'clock, or every Tuesday from 9 till 10. That's one concept. So we can make an object for that. So now we have this combination here, which says Anna teaches IT. And we have the cell itself, in this case, Monday 10 till 11, the period. So the fact that Anna teaches IT at Monday 10 till 11, that concept, we could also group that as a value object, right? So we can combine these two things that are compositions themselves and also combine this. So we're basically saying that this class is taught at in this period. In a sense, we have some concept of identity here. The identity is the fact that it happens at this point, and what happens at this point, that's sort of the value. So the period becomes the identity for the class happening in the period, if that makes sense. Yeah? It's all very simple, really. This should all be stuff that you can sort of naturally understand. So here you can sort of see that, well, what I just explained, basically. The blue ones are the period, and the red one is the class. So, and then the combination of everything, that's the green one here. Jim teaching English at Monday 9 till 10. That is the sort of complete. You could call this maybe a scheduled lesson or a scheduled class or something like that. That could be a good name for it. Maybe there's even a better name, and you can sort of search for it. So I lost count how many we have now. I think about 11 or 12, something like that. Let's find some more. Who's still in the game? Who still has we had like one person who had 11, right? So, okay, great. You win, by the way, or you're close enough. So let's find some more combinations. How about the whole thing? These two things. So we have this concept of something identifying something else at a position in time. That's what we did with the period. Here we have something similar. So this whole schedule, the whole bottom blue circle, that's a lesson schedule. That could be the name of this object. A lesson schedule is composed of scheduled lessons, and scheduled lessons are composed of lessons or classes at a period, and periods are composed of things. And so this becomes very fractal, but that's very nice because everything is sort of nicely encapsulated in its own concept. We haven't used any arrays yet. Yes. So now we have this sort of same idea at a little bit bigger structure. This lesson schedule here at the bottom, this is only valid for a very specific group of people. It's valid for people in group 1A, but not just any group 1A, the group 1A in school Hogwarts, and not just any group 1A in school Hogwarts, but only 1A in Hogwarts in a specific school year, right? So these things, the top things, I'm not sure how we could name that one. Let's say, so it's a school and a school year and a group, so that could be, I don't know, maybe just call it group identity or something, because it's not just the group label, it's not just 1A, but it's this very specific group in this school year in this school. So for this specific group in a school year in a school, we have this specific lesson schedule, right? So these are also two value objects, very complex. Well, so they're still very simple, really, if you look at them. And one sort of identifies the other. One defines where the other one is applicable. So if you were to build something like this in code, the top thing, or if you were to build like a relational schema for it, the top thing could be a composite key. That's basically what it is. This top thing is an identity. It's a composition of elements that together they are unique. Like there are no other Group 1As in 2014 in this school. So you know exactly which one you're talking about. It's a natural identity. This identity comes from things in the domain, right? This is just things that are there that we use to identify something. And this is how people in the domain would talk about it. They don't, for some reason, humans don't like to think in UUIDs. I don't know why. But so we have these two concepts. And then of course the combination of the two things, that could be like, so if this is a lesson schedule, and this is a group identity, and this is then maybe I don't know what we could call this really. We didn't actually go that far in the code, but you could map these things together in one object. So depending on how far you want to go with this, I think we're now at 13 or 14 objects. So that's fun. We have lots of small objects. We have some problems though. There are things in this picture. So I said that that value objects are immutable. So if I have this whole structure here, there's no room for change. There are things that could change here. Basically, if you start thinking about it, a lot of what we do, a lot of software development is basically managing changing things. If you start to, like, something is not there and then something needs to happen and something needs to change. And we're constantly managing workflows and processes to make things change in the right way and to store the consequences of changes. So change is actually a very important, like sort of hidden concept in everything that we're doing. We're building systems that run over time. We're not building systems that represent one point in time, one structure and never changes. That would be very boring software. We're building things that help people in a business make decisions and make the decisions for them in many cases. And these decisions happen over time and they are different depending on changes in the domain, etc. So here there's something that can change. There's a couple of problems. Like if we identify Jim with his name, or maybe his full name, and I said in the beginning, a good identity is something that is stable and unique. Now, and that worked for the top thing. Like the school is not going to change its name. Actually, schools do change their name, but they will never change their name during the school year. It will be planned. They will say, okay, starting next year, September, the name of the school will be something else. Of course, the school year is not going to change, and the group name, same thing. They're probably not going to change the name of the group. So this combination, this composition is stable, and it is unique. In the case of Jim and Anna and Jack here, they are not necessarily stable, because people change their names. People change their names when they get married, when they're, well, running away from the law, maybe, when they have a sex change. But all these things happen. This is normal. So this is not a very stable identity. It's also not a very unique one, because people have the same names. There's many people who have the same name, so we cannot rely on that. If it was just for one school, maybe it would work. But if we're building a system for hundreds or thousands of schools, of course it doesn't work. So we could find some natural identity for these to identify. So basically, this model doesn't work because of this little problem here. So we want to make sure that we get the right person for the right group. So how do we deal with it? We can replace this with some value that represents this teacher that is stable and that is unique. We could look at natural keys, natural identity. So what could be a natural identity? From our point of view, maybe a social security number. That works quite well. There's a little bit of problem with this kind of, with using a social security number here for identifying the teacher, because we might not have it. Maybe it's a new teacher and we've already planned them in the system, but we don't know their social security number yet. They have to bring that with them the next time they come. Like they forgot their identification papers when they came at the interview or something. or maybe we're just planning things before we really know who's going to take it. So we might not be able to rely on it. So what we often do in systems, of course, is in software, is to generate a pseudo key, a pseudo identity. So this is a value that we just made up. Could be, well, here it's a UUID, except that I didn't have the space for it, so I made sort of a short version of it. Could be an auto increment. Auto increments are nice because you can sort of see ordering, but they're not really that safe to rely on. If you really want ordering, you have to store it separately. Other problems with auto increments is that you have, whatever you do, you always, when you create something new, you have to go to the database and then come back before you have an identity for this concept, which might be fine in many cases, but it gets really annoying, especially if you make very fast, responsive, rich client applications, where, for example, you want to enter some information, send it to the server, and then already start doing things with this new entity that you made. Maybe you entered a new teacher, and you already want to start assigning this teacher to lessons before even the server comes back to you with an ID. So if you generated the ID or assigned the ID, a UUID, on the client side, you already know who this person is before they are even persisted in the database. So that's one of the benefits, I think, of UUIDs. Another benefit is that they are not just unique within the context. So it would not be, if this is a teacher ID, an auto-increment teacher ID would only be unique for all the teachers in our system, in our database. A UUID is, there's so many possible combinations that you are, in practical terms, almost guaranteed that it is globally unique. They call them universal IDs for a reason, or globally unique, universally unique or globally unique IDs, depending on the UUID or GUID. There's more combinations of UUIDs than atoms in the universe. So the chances of collision are very, very slim. So that's another benefit. Why is this so nice? Because if, for example, I need to merge data, if I have maybe two groups of schools joined, and now we want to merge the teachers from one group of schools with the others, if they both have UUIDs, this is very simple because you don't have to assign UIDs to them. With auto increments, you would have a lot of clashes there. So here we have replaced, we still have conceptually the exact same model, except that instead of using teacher names, we're using teacher IDs as a representation of the identity. These little things here, they are values. What do we do with values? We wrap them in a value object, right? So we can actually, this is something that I've never seen done in PHP code actually, but this is very easy to do. You can wrap all your UUIDs or all your auto-increment IDs or any other kind of IDs that you have. You can also wrap them in a value object. This one would be called teacher ID. I wouldn't call it UUID, I wouldn't give it a generic name, because if I call it teacher ID, I get a lot of benefit again. I can type hint against an ID. That means if I have a method saying, for example, add pupil to group, and it takes a pupil ID and it takes a group ID. Have you ever had the bug where you switch those accidentally? Who has ever had that bug? Yeah. Probably more, maybe, actually, I would argue that you all have that bug somewhere, but you just don't know about it. They're very hard to find these kinds of issues. Can take a long time before you even detect that there's a problem. Maybe it just happens occasionally. With type hinting, you prevent most of these problems, because if I swap pupil ID and group ID in my client code, in my method call, then PHP is just going to crash on that. So fail early, fail often. So IDs, identities, they're just objects, just like any other. Because we now have, there's not a lot of behavior attached to IDs most of the time. Could be in the case of the 1A. 1A could, if that is a value object, the group label, that could have some behavior in the sense that we could ask, what grade are you for? And then it would reply 1. Again, that's a very simple calculation, but at least it's encapsulated. With this thing, there might not be a lot of behavior, maybe some validation, like does this even look like a UUID? Again, that helps to prevent the kind of problems where we would maybe accidentally inject an integer or some other value, some string that doesn't look like a UUID. Then at least we would catch those kind of bugs or those kind of mistakes. But more interesting, we have encapsulated the concept of identifying this teacher, which means that if we change how we identify teachers, the rest of our code doesn't care. And I've actually had this. I've actually done this with legacy code that was using auto increments everywhere, and that was getting us into problems. So what we actually did, we first wrapped all the places where teacher ID and all the other IDs were used. We wrapped them in a teacher ID object. They were all auto increments. They were all integers. And then we changed our implementation to use, for new teachers, it would use a UUID. For old teachers, it was still using the integers. We could even check on that. We could even, we knew like the number of teachers we had in our database, so we knew the maximum number of the highest possible integer. So this value object could even check this. So this teacher ID object could check, is this integer higher than 2,520, for example? If it is, then something has gone wrong, because there shouldn't be new teachers with a higher auto increment. And then for all the other teachers, of course, it was using a UUID. And the rest of the code didn't care. The rest of the code was still dealing with teacher ID objects, didn't care what they look like, didn't care what sort of shape they had. So this is how encapsulation helps you to prevent, to protect you or protect the rest of your code from change. Again, this is a very common principle in object-oriented. If you look at all the solid principles and a lot of design patterns in Gang of 4, a lot of those ideas are about protecting the rest of your system from change in one place. So that's what we're doing. If for none of these things the business rules are very complex, but if suddenly the business rules for temperature would change and Kelvin would be 275 instead of 273, then we would only have to change it in one place. So we're protecting ourselves from change. Well, that's sort of a bad example, but if the rules for school years could change, that from now on the school year starts on August 15, for example, the rest of our code wouldn't know this. We would only have to adapt one place. So the problem that we now have, of course, if we have this structure, this structure that represents a lesson schedule for a certain group in a certain year, a certain school year, but we now only have a teacher ID in here. And you know, as I already mentioned, people don't really like remembering who this belongs to. So when we are visualizing this, when we are making a view for this, if we are maybe rendering a PDF to print this, then we don't really want to show it like this. This wouldn't be very practical for people. The thing to understand here is that what I'm describing now is purely a presentation problem. This problem has nothing to do with the domain model. The domain model is complete. The domain model is still showing, tells us exactly who is teaching what at what point in time, etc. So there's no problems with that. If we add information to this, that would be sort of mixing concerns, because if we add the name of the teacher back in here somehow, we're actually doing this for no other reason than presentation, right? So I would argue that the name of the teacher in this model is not part of the domain model, it's purely part of the presentation here. So if we implement code to visualize this, to render this, the teacher name would not come from this object. We couldn't ask this object, hey, give me the teacher name as well, I needed to render it. We can only ask for the teacher ID, and then we have something like a widget or an HTML helper or something that knows how to map UUIDs to teacher names. It has some lookup table or it does some query somewhere, but that has nothing to do with the model. That's not part of the domain model. And this is something where people often mess up and start coupling everything to everything. There's no reason for us to couple to the concept of teacher in this model. We only need to couple to the concept of teacher ID. We only need the identity. We don't need the whole teacher for that. So it doesn't make sense to try to fit that together. we take this object, we give it to something that renders it, it sort of loops over all the things and puts it in the right place, and for every ID that every teacher ID that it encounters, it makes some kind of query to map it. If you're thinking now that this would be not very performant, there's millions of ways that you can optimize this. So it's not a performance problem at all. It's sort of a coupling problem. It's a problem of separating domain logic, which is about, in this case, about identity, separating it from presentation, which is about providing more user-friendly ways of identifying somebody than a teacher ID. Still making sense? Yeah? Great. How much time do we have? Oh, should be fine. How long do I have? 6 minutes. Okay. 15 minutes. Great. That should be fine. So we still have some problems here. This is all still very static. We're basically assuming now that there will be only one lesson schedule for one class in one school year in one school. In reality, it's not always like this. So we could sort of improve this model and introduce, so we're still, like, now we're sort of at the point that we need to ask ourselves, is this still a value object? A value object is immutable. Or is this becoming an entity? It is in a sense, because the top thing is the identity for the bottom thing, right? So that sort of makes it an entity already, but it's still immutable. And even with entities, I like immutability. It gives me a lot of power. There's, by the way, this top thing, if this becomes too complex, because we now have a composite of 3 values, we could still replace that by some ID, of course. But so the problem that we have now is that maybe this lesson schedule will change. There could be, and this is where you have to start asking the questions about change, right? When does it change? How often does it change? For what reason does it change? Who changes it? What are the consequences of change? And we have to ask the domain experts, and we have to figure out how they deal with this, how they reason about this, how they usually work with this, how they would do this in the paper world. So, and there's a lot of things that we can learn about this domain. For example, would this change? I've asked this question to the domain expert, and they said, what, are you crazy? If we change this, then we get 1,000 angry letters from parents. They only change this schedule maybe once every 10 years. And even then, they are very careful about it, and they announce it a year in advance. So this doesn't really change, not during a single school year. The number of weekdays, Monday till Friday, that doesn't really change, of course. But what could change is there could be ad hoc problems. There could be, it's Monday and, well, now I need to map it. I think this was Jim. Jim doesn't show up. He calls in, I'm sorry, I'm sick. We need to make some ad hoc adjustment. We could, like in software, we could just say this is a change to this thing. But if we think a bit more about this model, this is not just any change. This is a very specific kind of change. This is an ad hoc change that only happens once, and then hopefully next week the situation will have been resolved already. So is this something that we need to enter into this system, that we need to publish, that we need to send to all the parents and all the pupils, and that we need to print out and hand out to everybody? No, that wouldn't make sense. This is something where on Monday morning, somebody from the administrative staff would go to the pupils and say, oh, kids, we're sorry, there's no English this morning. Yes. But we have some other substitute teacher for you. Oh, damn. So this would not be part of our system, probably. This would not be changed in our system. So far, we're still good. But there might be more fundamental changes. For example, Jim, this was Jack, is going, is retiring in January. Or maybe Anna is pregnant. These are things that we sort of know in advance. We know, okay, starting November 1st, we will have to change this schedule. So this is not, if you start to think about it, we're not really changing the schedule. We're not changing things the way they are today. We are planning a change in the future. So the current schedule is still applicable, and the next schedule will become applicable at a certain point in the future, November 1st, for example. So this is not mutation. This is not changing the schedule. This is, in fact, a new schedule with a new identity. A new schedule that will replace the existing schedule at a certain point in time. And we know because we did ask the questions. We asked who changes it, what changes, why do they change it, how often do they change it, under what circumstances, what are the consequences. So with this kind of change, with this kind of major change, we would announce this in advance. We will say, so that's the consequence. We don't change the current schedule. We create a new schedule which has a new identity. So this applicability period in this example becomes part of this identity, right? So the whole identity is now 4 things. It's the 3 things we had before and a start date from which point on this schedule will be applicable. So we basically have 2 versions of the schedule, both with their own unique stable identity, right? So we can still, even though this thing, I would argue, is an entity, it's still sort of immutable. It has an identity. The identity is stable over time. It is unique. In this case, we managed to model it even without ever changing the actual schedule. We simply replace the schedule with a new version that we schedule in the future, right? So this is sort of one way of starting to think about these kind of problems and starting to model them. And like if there's nothing else that you start changing in your code when you go back to work on Monday, the one thing that I would recommend you to start changing, despite all the great advice of my colleagues here, would be to start using value objects. They're very cheap, they're very simple to use, they help you to structure your code and make it very flexible, have these small little things that can interact with each other and that you can pass around and that they never change beneath your feet. That makes it very, very powerful. And they sort of help you build bigger structures and bigger models that handle more complexity, because the way to deal with complexity is to find these little abstractions and then build abstractions upon abstractions, and that's what modeling is about. So that's what I would recommend. Try to find, like in this system that I worked on, we found, I'm not sure, somewhere around 70 or maybe even more value objects. Any kind of little thing that we found, we put in a value object, and it starts, attracting this behavior and grouping things and become composable and reusable, and you can have polymorphism, and you can have all these great benefits of real object-oriented programming, not procedural, not sort of faking object-oriented with procedures wrapped in services or something like that, but real, actual objects. Are there any questions about this? Was that hard or that easy?
Hello. How do you map this to database, or how do you do the mapping to?
Can we close the door, maybe? Thanks. Can you repeat the question, please?
Hello. Yeah, it's okay now. How do you map this to DB, or how does the relational mapping works with value objects?
There's a couple of ways to do this. If you're using something, are you using something like Doctrine? Yeah, okay. So first of all, we started by just doing sort of a little bit of analysis model, and of course we moved it into implementation model, which is our value object. In the end, this whole thing would probably, if you map this to a relational system, would probably just be a bunch of records. Like each of these could be a record. Each of these scheduled lessons is a record, so it could be an entity perhaps that is identified by the composition of the time and you can play with this. You can have different ways of doing this. You can make composite fields, but you can also group things in. For example, this representation here. So I said that this was one value object combined of 2 value objects. But we can represent this same value, this same bit of information with a string, the way I did here. This is a string consisting of a number of characters. I can very easily parse this string back into a value object, or render this value object back into the string. So it might be fine to simply store this value as a whole in one field in a database. The cost is just a bit of parsing, so that's not a real big problem. If you don't have to query on these values individually, then we don't have to normalize it. Normalization is a very good tool. Database relational normalization is a very good tool, but we don't have to apply this everywhere. So in this case, I would simply store this value as a string in this way. These I would just store as a string as well. Well, these are IDs, of course. The subjects I would just store as strings. Maybe some of these as well. Well, the school year, I would probably just store the integer of the starting year. I can calculate everything from it. So it's perfectly fine to do these kinds of things. If you need to, then of course you can change this schema to store the times separately. But I cannot really imagine that you would have to do a lot of queries on this sort of stuff. And so, well, the thing is, you can sort of, like, where do you do this? With Doctrine, there's some ways to do it, like types and embeddables, and there's ways to deal with that, but you actually don't have to. You can, maybe I should switch to some code. Where's my, oh, there it is. So, for example, here, if I had, I need a free hand. Wait, I need to, just a second, I will change my display configuration so I can actually see what I'm doing. And yes, so let's say I have, well, let's take this example, and let's say I have an entity called product. It's kind of hard doing this with one hand. No, let me just put it there. Thank you. Where's my, no? Okay, so let's say we have a private property here that is price, and we have a constructor that takes the price for a product which is a money object. We could do it like this, and now this price object contains the whole money value object. But we can also simply expand this and say that basically extract, so this would be something like get amount, and maybe there's a currency as well, get currency. So we're splitting this out, and then when I have maybe a getter on this thing, get price, the contract should still be the value object. So the outside of my code only deals with value objects. So I can do something like this, make a new money object using this amount and this currency, right? So if you look at this code, you can say from the inside, hey, wait a minute, you're not using value objects. Nobody cares. It's only on the inside. The outside of this code, the rest of my system, when it talks to a product and it constructs a product or calls a get price or something, it's always getting money value objects, so it's fine. You know, this is part of my domain model. Internally, I now have an alternative representation. I can easily map this to two fields with Doctrine. This is trivial. But my interface is still guaranteed. I haven't changed my actual interface. I could do something like this as well. This, let me just put this down. So I could say this price is maybe cast this to string, like this. And then here I could return money parse this. Okay. So this code now, of course without the first two ones, this code now has the exact same behavior as my previous version. It still has the same interface, it's still respecting the same contract, and I just chose a different internal implementation. So in this version, I would store the price as an ISO code, as an ISO representation, something like this. That's a universal way of representing a monetary value. So I can easily parse this back into money object. Again, this is trivial. You can do the same thing with the examples from the lesson schedule. So don't allow your framework or your libraries to fool you into thinking that something cannot be done just because they don't support it natively. I mean, Doctrine supports all of this natively. If you think this is waste, that's probably not true, because when you call this and then later you call get price, in between you're probably in a different PHP request with, so after this you will probably store this in a database, and then in the next request get it back out of the database. So you have to build the objects anyway. And usually Doctrine is doing this for you. Doctrine is hiding the work for you. Here you're doing it yourself. This is probably even going to be more performant than any sort of generic solution that Doctrine can do with embeddables. And it's less work to write this. It's very obvious. It's easy to understand. You don't have to learn an annotation language or anything. So, don't go overboard with your frameworks. That's the short version. And you can be creative in how to map this stuff. Any other questions? Yes?
Out of your experience, what other issues can you run into when using auto-incrementing IDs for identity tracking, other than merge conflicts?
So issues that I have with UUIDs or issues with auto-increments?
Auto-incrementing IDs.
Well, the things I mentioned, I guess, the fact that they're not globally unique. Because merging is just one example, but if you, for example, you're debugging something and you see 7, is this, teacher 7 or pupil 7 or something else, you don't know where this number comes from. If it is a globally unique value, then you have very strong guarantees that this you can find this. If you have to, you just look through all your tables, but you will find it somewhere. So this kind of thing. If you have a number, if you have a UUID and it doesn't exist in your database, then you know that something has gone seriously wrong. Whereas if you have an integer and you cannot find it in your database, you still don't really know where the problem happened, right? It's easier to figure out, to debug things this way. It's my experience. There might be more benefits. There will be some drawbacks. It's a little bit, UUIDs are a little bit bigger, of course. They're basically very big integers. So yeah, there's just see what works for your problem, of course. Okay, thank you very much.